This is actually a good one. All right, so we've got a rectangle, vertices, let's see, one side drawn along the x-axis here. The others are, and I have no idea what that curve even looks like. I have no idea, but it doesn't really matter because 2 points on here make up, right? Yeah. No, it's what? Drawn with one side along the x-axis, here to here, and two vertices on the curve. Well, how's it going to do that? The graph, that graph. But this is a non-calculator, right? E. Why do I not have an E button on here? Maybe it's EXP because it's with the logs. It is. E to the negative. Oh, I see what you're saying. Since it's symmetrical, it'd have to go on either side. Okay. There's my rectangle. The area of the largest rectangle that can be drawn with one side along the x-axis and two vertices. Okay, well, the area of this, how do I find an equation for the area? This is y equals e to the negative x squared. I am going to take a derivative, but I first have to find the equation for the area. So length times width, right? Or height times the width here. So let's think about it. The height, this is going to be the height, right? You agree with that? Times the width. And if I'm spanning that way, I'm going to have to do two x's. Right? Right. So now the derivative of the area with respect to x would be derivative of the first, chain it, times the second, plus the first, times the derivative of the second. I need to know where that equals 0 so I can maximize it. The only way that's going to equal 0 is if that, no, that's never going to equal 0, right? So that only leaves this to equal 0. This is how you did it? Or you just didn't know where to start on that? Plugging back into the derivative equation. I'm going to have a positive times, say I did -5. That's going to be negative. At 0, it's going to be positive. And then it's going to be negative again. So it's got to be happening at square root of 1/2. It's maximum. So if I plug that back into the area equation, e to the negative square root of 1/2 squared, 2 times the square root of 1/2. All right, squared, because let's see, square root of 1/2 is going to be 1 over square root of 2, which is square root of 2 over 2. Well, my answer's not on there. I got dangerously close, though. Oh, yeah, it is A. I did get it. You're right, because there it is. Yay, me. Did you follow that, though? It was hard. That one was hard. Because it said maximize area. So whatever you're trying to maximize, find the derivative of that, and then do your sign analysis. So the derivative of the area, set it equal to 0, and find the max or the min there, depending on what you're asked for. Right. And then plug it back in to find the max area, because that's only telling you where it occurs, not what it is when it occurs. Yes. Number. Hope it's easier than that one. The volume of a sphere is given by 4/3 pi r cubed. Use a tan line to approximate the increase in volume in cubic inches when the radius of a sphere is increased from 3 to 3.1 inches. So what am I doing? Let's see. We're going to find the equation of the tan line, and then we're going to plug in 3.1. We're going to plug in 3, and then we're going to plug in 3.1, and we're going to subtract the 2, it looks like. On there's what? Okay, let's see. Oh, in my head, I was like, I know it wrong, but I put I got Gotcha. Keep going. Okay. If I multiply by 3, I get 4 pi r squared. Right? All right, so it asked me, I lost my place. Tan line to approximate the increase in volume in cubic inches when the radius of a sphere is increased from 3 to 3.1. So we'll do at 3, so V prime of 3 would be 4 pi times 3 squared, which will be 9 times 4, 36 pi. That's my slope. I also need a point, so I'll do the actual volume at 3, which would be 4/3 pi times 3 to the third. I think I'll do this. How did I get the same thing? All right, so y minus y1 equals slope times x minus x1. What happens if I plug in 3.1 here? For x. $39.6 pi. How is that different from the actual volume at 3? Did they get D? 3.6 pi or 3.6, yeah. Okay, let me just, all right, so our original function, the derivative, and the second. Straight up just the way they sit, right? This is my slope of the original function. It tells me the maxes and mins of the original function. This is where you do the sign chart. You do positive, negative, increasing. And it tells you if you have a max or min on the function, right? These happen at zeros of the derivative, right? So if I look at where this crosses the x-axis, it'll tell me possible maxes and mins of the derivative, of the function. Second derivative, which can tell me the slope of the first derivative, because each derivative can tell you the slope of the previous. Okay. It also tells me the concavity of the function. So this is where I do second derivative, tells me what the first is doing. A positive negative would be concave up, concave down kind of thing. Yes, again, this happens at zeros of the second derivative. That makes sense? Yes, but you have to be able to really interpret and go back and forth with them depending on what you're given. The most straightforward is given the derivative, tell where the max or mins happen, or vice versa. But as you start really working with it, we're looking for maximums and minimums. So derivative of x would be 4x cubed minus 4x. I'm not sure why. What? Okay. So leave me with x squared minus 2. So this is plus or minus square root of 2. The derivative. That's why, so I get confused with that too. That's why I put derivative down here, so I remember I'm looking for the sign of the derivative to tell me what the function's doing up here. So if I plug in -1, that would be -4. Oh no, Stacy. Okay, so I'd get -4. We'll say, so that'd be positive. Of course, it's dragging now. Whoa. Then if I put +1, I get 4 minus 8, which is negative. And then a really big number is, of course, going to be positive. So I got 2 minimums and 1 maximum. What did they do with it?